All right, here we go. So this is problem number 12 from section 5.2. We've got block B in the figure here. It tells us that it weighs 711 newtons. So let's make a little drawing here for block B. It weighs 711 newtons. So I can put in my force of gravity, negative 711 newtons. Let's see. It's sitting on a table, and the only other forces on it are vertical. So I feel like we can put in our normal force here. That's got to be 711 newtons, right? And then there's this tension force pulling it forwards and friction holding it backwards, right? All right. So it tells us that the coefficient of static friction between the block and the table is 0.25 newtons. Our question is, I guess I sort of got ahead of the gun here. The question is, what's the biggest mass we can have here such that nothing moves, right? Well, so our concern is that we want to make sure that B doesn't, slide across the table, right? So we are going to put to use our static friction, and since we're trying to maximize the mass, it makes sense to maximize our static friction, right? So let's do that. Our force of friction static max in this problem is our coefficient of static friction times our normal force, which for us is 0.25 times 711 newtons. So multiply that out, and you get 177.75 newtons. So that's our maximum static friction. So let's assume that our tension is meeting that, right? Okay. So if we are just putting block B on the cusp of moving, this is what block B looks like. Okay. So now let's take a look at what's going on from the perspective of this knot. Okay. So at this knot, what's happening? Well, there are three forces on it. There's this tension force. Now remember, the tension at both ends of that rope are the same. So if it's 177 here, then it's got to be 177 here. Okay? All right, and then what other forces are there? Well, let's see. There's the force of tension from A pulling down. So let's just call that the force from A pulling down. It's a little bit sloppy. How about if we do this? The force of tension produced by block A. How about that? All right? And then there's this other force over here, this guy, right? Right? But the idea is that's going to have both a horizontal and a vertical component, right? So let's call this, I don't know, I'm running out of letters here. Let's just call it force R for rope. FR as in force of that other rope. Okay? So that other rope is going to have an X component and a Y component, right? Well, that knot isn't moving, right? So that means that the X component of the rope has to be 177, oh man. Let's try that again, Cornswoggle. So that rope has to be 177.75 newtons in the X direction, right? So that our X components cancel out, right? Okay, and we're told that this angle here is 30 degrees. So I feel like we can do a little bit of trigonometry here, right? So let's see, we've got this triangle here. This is 30 degrees. Oh man, 30 degrees. We know that this is 177.75. So we ought to be able to use a little bit of, we can use tangent to find this other guy. So, if you find this guy, it turns out to be 102.6. Okay, so that is the Y component from that rope, 102.6 newtons. Okay, just by using a little bit of trig on this. All right. Oh, well, that means that the tension pulling down from A has to be 102.6 newtons. Right? And that accomplishes just putting it on the cusp of moving. So now if we erase this guy, now that we've got that all done, now let's take a look at this block A. So here's block A. So the idea is if A is pulling down with 102 newtons, then A must be being pulled up. So the force on A from the tension is 102.6 newtons. So that means our force of gravity must be 102.6 newtons. And so we can find the mass by just doing that divided by 9.8, and we get 10.5 newtons. So just 10, or kilograms, sorry. So it looks like on the answer key, for some reason I rounded off to 2 sig figs. All right, so there you go. If you're keeping score, it's actually like 10.47 kilograms. All right, so there you go. Oh, I forgot to hit stop. I'm hitting stop now.